All right, guys, here we go. First video lecture, section 8.1. Chapter 8, in my opinion, is some of the best stuff we do in this class, and unfortunately, it's some of the stuff that students tend to do the worst on. I'll admit, it's a little hard to grasp at first, because it's almost like we're doing, in Chapter 8, it's almost like we're going to be doing meta probabilities. It's like, in the past, the types of probabilities we've looked at have been probabilities of, like, what's the probability that a single event occurs, right? Whereas what we're going to be looking at now is, what is the probability that you get a sample mean or a sample proportion of a certain amount? And so you're looking at, out of a sample size of 100 individuals, what's the probability that the sample mean will end up being some value? And so that makes it a little more challenging. It makes it a little bit more abstract, and that's something that I think tends to kind of mess students up a little bit. But to give you an example of why we want to talk about these kinds of probabilities. These are the kinds of probabilities that are going to be the most useful for us when we are trying to perform inference. So this chapter, section 8.1 and 8.2, these two sections are really what prepare us for the rest of the semester, okay? So to give you an example, right? Let's say we want to determine if a particular fertilizer causes corn stalks to grow taller. So we might set up an experiment, right, where we apply the fertilizer to a plot of corn stalks, wait a few months, and then measure the height of those plants. We would then probably compare those heights to the heights of some corn stalks that didn't have the fertilizer applied to them or something. And if the average height of our plants with the fertilizer is significantly larger than the average height of just corn plants in general, then we would say that, yeah, the fertilizer is effective at causing corn stalks to grow taller. But the question is, what exactly do we mean by significantly more? Like, if the average height of all corn stalks is, 6 feet tall, would it be unusual for our corn stalks to end up with an average height of 6 foot 1.5 inches? Right? These are the kinds of questions we want to be able to answer. And so the probabilities that we end up wanting to compute are probabilities involving the sample mean x bar. In this particular case, we want to be able to compute this probability, right? We want to be able to compute the probability that our average height, we want to be able to compute the probability that we would get a sample mean at least as big as ours if in fact the fertilizer were ineffective. If that probability is really small, then it casts doubt on the assumption that we make here in this condition, right? It casts doubt on the assumption that the fertilizer is ineffective, and so then that would mean that the fertilizer is in fact effective at causing corn plants to grow taller. Okay, so so that's kind of the moral of the story, right? We want to be able to compute probabilities involving x bar, right? The sample mean of a bunch of observations rather than just a single observation. Okay, so we want to compute probabilities involving the sample mean of a bunch of observations. In order to be able to do that, we need to know what kind of distribution x bar has, right? So we need to know, is it a binomial distribution? Is it like a normal distribution? Is it some other kind of distribution that we haven't talked about? Because then that's going to tell us which calculator we can use in StatCrunch in order to compute probabilities involving x bar. Okay, so in order to figure out what the distribution of x bar is, we need to look at what is the average of all of the sample means. So if you were to take all of the possible sample means and then take the average of those sample means, what is it, right? So what's the center of the distribution? What's the standard deviation of the sample means? So if you took every possible sample and took the sample mean of those samples and then computed the standard deviation of the sample means, what would the spread be, right? And then we also want to look at what is the shape of the distribution. So those are the three keys that we want to be able to look at in this section. We want to be able to look at the shape, center, and spread of the distribution of x bar. So the distribution of the individual sample means. So we're going to kind of think of x bar as a random variable, okay? And maybe to give you a concrete example, let's say that the government wants to determine the mean of all U.S. household incomes. So they might go out and survey some households, right? Now, maybe they don't get information about every single household in the United States. So one sample that they get might have a sample mean of $67,976. And another sample might have a sample mean of $67,731. And another sample will have a different sample mean still from the other two, right? And every time you collect a new sample, x bar is likely to be different from the previous ones. So since x bar is different from sample to sample, x bar is a random variable. We want to be able to identify the shape, center, and spread of the random variable x bar. That's what the sampling distribution of the sample mean is, right? So the sampling distribution of the sample mean just lists off the possible values that x bar can take on, together with the probability that x bar takes on that value. So it's just a probability distribution, but for x bar, right? So for a sample mean of a whole bunch of observations rather than just a single observation. So let me give you an example of this. Okay. So this one says, James, Lori, Kate, and Clint live together in a household, and they share a data plan through their cell phone company, which charges by the gig. I don't think cell phone companies do this anymore, right? Maybe they do, but anyway, the chart below summarizes the number of gigs each member of the household uses per month. Part A asks us to compute the population mean. Now in this case, that's easy because we have all of the members of the household. So this is a really small population. And so we can compute the population mean pretty easily, right? We can say, well, we're just going to add up the values, divide by 4 in this case, right? Since there are 4 individuals in the household. So this would be 2.4 plus 3.2 plus 2.5 and so forth, divided by 4. Let's see what we get. Divide by 4. So I'm getting 2.45. Okay, so there's the population mean. Now part B says, write down all samples of size 2 and compute their means. Right, so here's our population, right? There are 4 individuals in the population. If we randomly select 2 of them, what are the possibilities? Well, one possibility is that we could end up with James and Lori. Another possibility is we end up with James and Kate. We could also end up with James and Clint. Those are all the samples that involve James, but we could have other samples, like we could have Lori and Kate. We could have Lori and Clint. And then finally, we could also have Kate and Clint. Right? So I think those are the 6 possible samples. So now let's compute their sample means. Okay, so to compute the sample mean for each of these samples, for James and Lori, right, we would say 2.4 plus 3.2 divided by 2, right? We're just finding the sample mean of that sample of individuals. I'm explaining this in words because I'm not going to write it down because I don't think I have enough space. I'm just going to write down the answers, right? So for the sample mean here, we're going to say 2.4 plus 3.2 divided by 2. So that's 2.8. For James and Kate, we can do 2.4 plus 2.5, right? Because James used 2.4 gigs, Kate used 2.5 gigs. So we say 2.4 plus 2.5 divided by 2, and that's 2.45. For James and Clint, we would say 2.4 plus, Clint used 1.7, right? So plus 1.7, whoops, 1.7 divided by 2. We get 2.05. Okay, so I think you see where I'm going with this. I'm gonna fill out the rest of them. Now the nice thing about these videos, right, is that you can pause, you can rewind, you can rewatch. So if you are having a hard time keeping up with me, just pause, right? Okay, Lori and Clint, 3.2 plus 1.7 divided by 2. Oh, I'm sorry. I think this one belonged. I think this one belonged over here with Lori and Clint. That's what I get for trying to type and talk at the same time. 3.2 plus. Yeah, this one should be 2.85. This one should be 2.1, this last one. Okay, so there are all of the sample means. So now the sampling distribution of the sample mean is going to list off those sample means together with the probability that x bar is that value, right? So it's going to look just like a probability distribution, only we're going to use x bar instead of x, right? So I'm going to try to put these in order from smallest to largest. The smallest x bar could be was 2.05. And then we had a 2.1. And then 2.45. Right, that happened twice. And then we had a 2.8. And then a 2.85. Right? Now the probability that x bar was 2.05, well, there were 6 possible samples, and only one of them had a sample mean of 2.05. So the probability that x bar is 2.05, 1 out of 6. Probability x bar was 2.1, also 1 out of 6. Probability x bar is 2.45, now that would be 2 out of 6, right? Because there are 6 possible samples, 1, 2, 3, 4, 5, 6, and 2 of them, right? 2 of them had a sample mean of 2.45, so 2 out of 6. Okay, that reduces to 1/3, of course. Probability x bar is 2.8, 1/6. Probability x bar 2.85, 1/6. Okay, so there is the sampling distribution of the sample mean. Right? It's just a probability distribution for x bar. Now part D says, what is the mean of the means? What's the mean of the sample means, right? Mu sub x bar in part B. Mu sub x bar. In other words, so what is the mean of these values here that we came up with for the possibilities for x bar? So what's the mean of the sample means? Well, let's see. If we add these up and divide by 6, right, that should give us the mean of the sample mean. So we're going to say it's 2.8 plus 2.45 plus 2.05 plus 2.85 plus 2.45 plus 2.1 divided by 6. Let's see. And we get 2.45, which is kind of interesting. If you look back at what we did in part A, the population mean we got was 2.45. Now we're saying the mean of the sample means is also 2.45. That's not a coincidence. That turns out to be true in general. And so you might think, well, then it's kind of silly to kind of do it this long way. But the thing is, we don't always know what the population mean is, right? And this fact is useful in and of itself, right? The fact that the mean of the sample means is equal to the population mean is something that will come up again. So I'm going to start a new video to do the next page so that it doesn't take so long to upload this to YouTube.